This is the second part of our three-part series on kinetics, and in this lecture we'll be talking about integrated rate laws. And if you remember what we talked about last time, just the basic rate law, they were in terms of a change in concentration over a change in time. Right? And so that dt, if you think about in terms of calculus, you can actually integrate these, and why you'd want to is you would get rid of the change in time, and you would be able to put these in terms of time, where you can actually find a concentration at any given time, or you can find a calculated time that it would take for a certain amount of reagent to be left. And that's kind of what these half-lives, where those come into play. So the title slide, I like this figure because it gives you a good overview and summary of integrated rate laws for 0, first, and second order. And in this class, that's primarily what we'll be dealing with, 0, first, and second order reactions. And so those are the integrated rate laws are shown up here, right? And we'll go through these again later in the class. But for the final, you can use a sheet of notes. So you really don't have to memorize these per se, but just make sure that these rate laws show up on your notes for the final, as well as the half-life equations, right? So the half-life is how much of your reactant is left, the time it takes for half of your reactant to be left in a given reaction. So this material is coming from section 4 and 5 of chapter 16. So let's first try a practice question, kind of review over what we talked about last time. Okay, we have a particular temperature and volume, two gases, red and blue, A and B, react. The following molecular scenes represent starting mixtures of the 4 experiments. Okay, and so you have 4 experiments, and then you're getting, you're shown here initial rates for all of them. Okay. What is the reaction order with respect to A, with respect to B, and the overall order? Write the rate law for this reaction and predict the initial rate of experiment 4. So to answer this, we need to write, it helps to write down what the concentrations are at all of these points, okay, and summarize it sort of in a table form like we were given in the previous previous problems in the previous lecture. Okay, so if we do our table, we're going to have a rate that they're given. Okay, so that would be for experiment 1, 2, 3, and 4. Okay, so the rate for experiment 1 was 0.5 times 10 to the minus 4. 2 is 1 times 10 to the minus 4. 3 is 2 times 10 to the minus 4. And then 4 is an unknown. Okay, and then we can also calculate how much A and B we have. So in A, we have 2 of each. Excuse me, in 1 we have 2 of each. In 2 we have 4 A's and 2 B's. 3 we have 2 A's and 4 B's. And then finally we have 4 and 4. So now we can look at what the coefficient of our rate laws are. So for question A, we need to compare, first let's look at the rate of experiment 1 and 2. So if we do rate of experiment 2 divided by rate of experiment 1, and in those 2 experiments, B is being kept constant, A is changing. Right, so A2 divided by A1, and then that would be to, let's just call it the M power. Okay, we're trying to figure out our rate law So that would be our rate law for this process, trying to figure out the coefficients m and n. So let's plug those values in now. We'd have 1 times 10 to the minus 4 divided by 0.5 times 10 to the minus 4 for the rates, so that would equal 2, and that equals the concentrations 4 and 2 to the m power. So here we have 2 equals 2 to the m power, so m has to be 1. Now we can do the same thing using the rate of experiment 3 compared to rate of experiment 4. And now we have the, experiment 1, not experiment 4. Concentration of B in experiment 3 divided by B in experiment 1. To the n power. And my pen is really messing up. Okay. So those rates, you have 2 times 10 to the minus 4 divided by 0.5 times 10 to the minus 4 equals concentration of B in experiment 3 is 4. Concentration of B in experiment 1 is 2. So here we have 4 equals 2 to the n power. So n has to be 2. Right, so then we can go back to our rate law and write those coefficients in. So our rate is going to be equal to k times a to the first power and b to the second power. Right. So that would be our rate law for part B. Write the rate law for the equation. A, we want to know the overall order, so it would just be 1 plus 2, that would be 3, so third order overall. And finally, part C, I'll just draw part C up here. Okay, so for C, we can calculate a rate constant. So our rate constant is going to be, let's just use the data in experiment number 1. So we have a rate of 0.5 times 10 to the minus 4, and that has to equal k times 2 times 2 squared. Right, so 2 squared is 4 times 2 is 8. So k is going to be 0.5 times 10 to the minus 4 divided by 8. So our k value is 6.25 times 10 to the minus 5. Oh, 6, excuse me, minus 6. We've used that data to calculate our k value. So the experiment 1 we've used to calculate a k value. Now we can plug in concentrations for experiment 4. So experiment 4, we can find the rate because we know k, 6.25 times 10 to the minus 6. and we can plug in values for concentration that were given for A and B. So when you do that, you'll find that the rate is equal to 4 times 10 to the minus 4. And that would be in moles per liter per second. Okay, so that's how sort of a basic kinetic problem will work. If you're given the experimental data, you have to first calculate the order that it is in for each reactant. Then you would come up with your rate law. Then you could use that to find a value for your K. And then you can use, once you know K and your rate law, you can find the rate at any given set of conditions. Well, it turns out that these rate laws, they're useful, okay? But what makes them more useful is when we integrate them, and then it introduces time into the equation. And when we have time in the equation, we can find concentrations at any given time for the reaction, or we could calculate a time that we need to let the reaction go till a certain amount of product is formed, let's say. Okay. So the first order rate equation is shown on the left here. Right, we have rate equals negative change in concentration of A over change in time, and we can write that as the rate constant times the concentration of A. When you integrate that, right, you don't need to know how to do this for this class. We won't be doing the calculus. All you need to know is that when you integrate that, what you get out is the natural log of A naught, which is the starting concentration, divided by the concentration at time t equals kT. Okay, for a second order, right, our second order rate is shown here. When we integrate that, we get 1 over A at time t minus 1 over A naught equals kT. And then finally, a zero order rate law is A at time t minus A naught equals negative kT. So the second order and zero order integrated rate laws look sort of similar. The first order is the one that you have to take the natural log of A naught over AT. So let's try a practice problem with integrated rate laws. Okay, at 1,000 degrees Celsius, cyclobutane decomposes in a first order reaction with very high rate constant of 87 per second. To 2 molecules of ethylene. Okay, so C4H8 is going to 2 C2H4. The initial cyclobutane concentration is 2 molar. What is the concentration after 0.01 seconds? Okay, and then B, how long will it take for 70% of the cyclobutane to decompose? Right, so in this is a case where we can use our integrated rate laws. So our reaction is C4H8 decomposing to 2 C2H4s. And we're given a rate constant of 87 per second. And an initial concentration, C4H8 initial, of 2 moles per liter, 2 molar. Right, so we can take we're told that this is a first order reaction, first order rate, and the units of our rate constant indicate that as well. So we use our integrated rate law from a first order reaction. So that is, remember back to that slide, it's ln of A naught over A at time t equals K times T. Right, so then we get, we can plug these values in, or you can sort of rearrange this equation too, however you'd like to. I'm going to plug these values in. So we have ln of A naught is 2 moles per liter, 2 molar, divided by our concentration at time t, C4H8, equals rate constant is 87 per second times the time we're given is 0.01 seconds. So to get rid of the natural log, you would do e raised to that power. So, right, if we have e on both sides raised to that power, right, that takes away the natural log. And we'd get e to 87 times 0.01 is 0.87. So e to the 0.87 power. Okay, and that equals, just plug that into the calculator, that equals 2.4. Right, so now we need to solve for our concentration. So our concentration of C4H8 at time t, which is 0.01 seconds, is going to be equal to 2 molar divided by 2.4, right, which will be 0.83. So that was part A. Okay, part B, we want to know how long will it take for 70% of that to decompose. So what we can do is say, okay, starting at 2 molar, 70% of that times it by 0.7 would be 1.4 molar. Right. So 1.4 molar is how much has decomposed, so 2 minus 1.4 will be what we're left with, would be 0.6. So that's the concentration we would have if after 70% has decomposed. So then we can plug that into our equation, our first order integrated rate law. So A naught was 2 molar, A at time t is 0.6 molar. And we know that that equals K times T. Right, so we can divide that by T, ln of 2 over 0.6, divided by T, K, which is, 87 per second. So we'd get a T value here of 0.014 seconds. So that is a pretty fast reaction. Well, you can find these some of these values graphically as well. And to do that, we plot the natural log of the concentration with respect to time versus time. And you get a straight line depending on, for first order, you'd get a straight line. And the intercept here is going to be the ln of your starting concentration. Your slope would equal your rate constant, the opposite sign though. Okay. And if you think about a straight line, it's y equals mx plus b. So y in this case is ln of at. M is the slope, so m here is negative k. X is t, and the intercept would be ln of a naught. So you can rearrange your integrated rate law to get a straight line form in the form of y equals mx plus b, and there you could pull these values from a plot. If we looked at a second order reaction, what we'd have to do is plot 1 over AT versus time. And then the same thing is true. We could take our integrated rate law for a second order reaction, convert it into a straight line form where we have y equals mx plus b. And a zero order reaction would simply be you're plotting concentration versus time. Okay. And again, integrated zero order rate law can change that around, rearrange it to give a form that would be y equals mx plus b. Okay, slope, again, in this case, just like a first order, the slope is going to be equal to negative k, negative the rate constant. So if we're looking at how you would do this experimentally, you'd plot versus time different concentrations here, like let's say this is our reactant N2O5. We would plot concentration versus time. You would plot also the natural log of that concentration versus time and 1 over that concentration versus time, and see which gives you a linear fit, and then you would determine whether or not it's zero, first, or second order reaction. Right, so here are those plots of that data. Zero order gives this shape, which is not linear, so it's not zero order. Second order as well, it's not linear. The straightest line that's given is for the first order, right? So there might be like a slight curve there because this is real world data, but you can see that it is pretty linear. So we can call this a first order reaction with respect to N2O5. One neat thing that the reaction half-lives, the reaction integrated rate laws give us are reaction half-lives, the ability to calculate the time it takes for half of our reactant to be gone. Okay. And I'm sure you've heard of that before. Typically, we talk about half-lives in terms of radioactivity, and that's a way that you can use, like C14, for instance. You can use that for dating purposes because you know how long it takes for half of the carbon-14 to decompose, and in living things you have a certain amount of carbon-14 all the time because you're constantly taking in carbon molecules, and as soon as something dies, it stops doing that, so then the carbon-14 will start decreasing in that sample, and you know how long it takes to reach half of that amount. So you can use that to calculate dates of things. Right, so for a first order reaction, the half-life does not depend on the starting concentration, which is kind of crazy. Okay. So when we look at the half-life, right, you could calculate these half-lives if you were just to take the integrated rate laws and plug in 1 as your starting concentration and 0.5 as your concentration at time t, and then solve for t. What you'd get out is the half-life, right? So a first order, the T1 half would be equal to ln of 2 over k. So the half-life in this sense for a first order reaction is constant because it doesn't depend on the concentration at all. Right? And radioactive decay, it turns out, is a first order process. So the half-life for radioactive nucleus doesn't depend on the concentration, so that's why it's useful. Right? You can see if you have a reaction that, like the N2O5 that we mentioned before, if we look at a starting point and waiting 1/2, so in this case a half-life is 24 minutes. So we start at 0.6, we go a half-life 24 minutes, we'll have 0.03. So we're going from 0.06 to 0.03. We've lost half of that concentration after 1 half-life. Right? If we go another half-life now, we're going from 0.03 to 0.015, okay? So our total time, that was from 24 to 48 minutes, so our total time now is 48 minutes. And we have 1/2 times 1/2, or 1/4 of what we've started with at the start, because we've waited 2 half-lives. So that'd be 1/2 times 1/2, which would be 1/4. And then finally another half-life here. We go 24 more minutes, and we wait. We drop from 0.15 to 0.0075. Okay. And so the total drop from the start would be 1/2 times 1/2 times 1/2, 3 half-lives after 72 minutes. Okay. So if you're trying to calculate, how much concentration is left after a certain number of half-lives, you can just multiply, however many half-lives you have, 1/2 times 1/2 that many times to give you the concentration that you're down to based on the starting concentration. So let's try a problem with half-lives. Substance A is green. It decomposes to 2 other substances, blue and yellow. And it's a first-order process. Okay, the molecular scenes shown below show the reaction mixture at 2 different times. So we have T0. So initially we have all A. And then at time equals 30 seconds, you can see that now we have only 4 molecules of A and 4 molecules of B and C. Okay, so we started with 1, 2, 3, 4, 5, 6, 7, 8, and at time 30 we are at half of that left. So this would represent 1 half-life. Okay, draw a similar molecular scene of the reaction at T equals 60. Find the rate constant for this reaction. And finally, if the total pressure of the mixture is 5 atmospheres at 90 seconds, what is the partial pressure of substance B? Okay, so our reaction that we're looking at is A goes to B plus C. And we can see concentrations, right? A naught is equal to 8. A at 30 seconds is equal to 4. So that represents a half-life. We've dropped it by half. And then B and C at 30 seconds, they're also equal to 4. So the first question, draw a similar molecular scene of the reaction at 60 seconds. So that would represent another half-life. So we would have 1/2 times 1/2 times the initial concentration of A, which would be 8. So that would be 2. And B and C, so we'd have to draw 2 green dots. And B and C now are going to go up by the same factor that A went down. So B at 60 seconds would equal C at 60 seconds. And that would be 6. Right? We started with 8, we've lost 6 A's, and we produced 6 B's and 6 C's. Okay, so for question B, find the rate constant for the reaction. So with the information we're given, right, we're given this experiment that basically showed us the half-life is 30 seconds. So we can use the equation for half-life that involves K. We can rearrange this to solve for K, right? It would be ln of 2 over the half-life, which is 30 seconds. So this would be 0.023. And the units would be 1/seconds. Okay, and then finally, for C, find the total pressure, or if the total pressure of the mixture is 5 atmospheres at 90 seconds, what is the partial pressure of substance B? So P equals 5 atmospheres at 90 seconds. Well, what is 90 seconds? 90 seconds is 3 half-lives. So if we do 1/2 times 1/2 times 1/2 times 8 for our starting material A. So 1/2 of 8 is 4, 1/2 of that is 2, 1/2 of that is 1, so that would just be 1. We're going to have 1 part of A at 90 seconds. And so if we started with 8 and lost 7 to get to 1, we're going to have to produce 7 B's and 7 C's. So whatever we lose in A, we make up in B and C. So to find the partial pressure of B, what's that going to be? We would take the parts of B, which would be 7 parts B, and divide it by the total number of parts. So if we have 1A, 7 B's, and 7 C's, that's 15 total parts. So 7 divided by 15. And then you would multiply that by that fraction by the total pressure. So 7/15ths times 5 atmospheres would be 2.33 atmospheres. Okay. Here's a question where we have to calculate a half-life. Cyclopropane, which is shown here as that triangular molecule, is the smallest cyclic hydrocarbon. Because its 60-degree bond angles reduce orbital overlap, its bonds are weak. As a result, it is thermally unstable and rearranges to propane at 1,000 degrees Celsius via the following first-order reaction. The rate constant is 9.2 per second. So we're told it's a first order rate. Rate law is given the K value. Now we have to determine the half-life, and for the second part, how long does it take for the concentration of cyclopropane to reach 1/4 of the initial value? Right, so that one, you might say, okay, well, it's going to take 2 half-lives to reach 1/4. Okay, but we need to know exactly what that half-life is to find what 2 half-lives would be. Right, so we need to remember our equation for half-life for the first order rate law. Half-life is going to be ln of 2 over K. So we're given K, so we can just plug this in. Right, so A, T1/2 equals ln of 2 over K, and K is 9.2. So that'd be 0.693 over 9.2, and that equals 0.075. And important to remember the units. So K it's a first order, so it's 1/2. So that half-life is in seconds. Okay, for part B, we're looking for 1/4 or 25% of the starting concentration. Just call that A naught. Okay, and that's going to be, you can do this one of two ways, right? You can say, oh, that's just going to be 2 half-lives. 1/2 times 1/2 equals 1/4. So we would take T 1/2 and multiply that by 2, which would be 2 times 0.075, which is 0.15 seconds. Okay, so that would be the easy way. But if you don't remember that, or you don't see that right away, you can use the integrated rate law. Right, so ln of A naught over ln of A t equals kt. And I should mention too, if you ever forget the equations for the half-life, you can just use the integrated rate law and calculate them and basically find them. It just takes an extra step. Okay, so for this, if we rearrange this to solve for t now, we'd have ln of A naught over A at time t divided by k equals t. And we know, we're being told that's 25% of A is left. That's what we need to find the time for. So what we can do is set A naught equal to 1, and if only 25% is left at time t, that would be 0.25. And then k is, again, 9.2. So that would be equal to, what's that, ln of 4 divided by 9.2. And that's going to equal 0.15 seconds. Right, so same thing. You can do it the long way, or you can remember the shortcut. Right, so we've seen that in a first-order reaction, the half-life does not depend on the initial concentration. Unfortunately, for zero-order and second-order, it does. Okay, a second-order reaction, the half-life is inversely proportional to the initial concentration. Right, so if we use our integrated rate laws and plug in, a value of 1 for Ka, and 1/2 for A, or 1/2 of A naught for A at time t, we'd get this expression. So our half-life for a second order is equal to 1 over K times A naught. And for a zero-order reaction, the half-life is directly proportional to the initial concentration. So the half-life is A naught over 2K. All right, this is a good summary table for everything we've sort of talked about for kinetics. It gives you, for zero order, first order, second order, the rate laws, how the form they would follow, the units that you would look for your K values, your rate constants, the units they would have, your half-life equations, integrated rate law equations in the straight line form, the plot you'd have to do to get a straight line, and then what the slope and the y-intercept are for those straight lines. Okay, so I think this plot, this table is probably a good table to have on your exam. Right, the only thing it doesn't have is the integrated rate law in the non-straight line form, but you could probably always just add that in. I think that would be probably everything you would need in this section of the book. We're going to briefly talk about some theories in kinetics, and one is the basic theory that we'll talk about is collision theory, and that's that particles have to meet in order to react. So increasing the concentration of the reactants leads to larger number of collisions, and hence you would increase the reaction rate. The number of collisions depends on the product of the numbers of each reactants, not their sums. So in other words, the concentrations are multiplied in the rate law, not added. So changing the concentration, even raising it just a little bit, gives you a big increase in the rates. And this is a graphical or a pictorial way to represent that collision theory, right? If we had two A's and two B's, 4 possible collisions with those, adding just one more molecule of A, now we have a possibility of 6 collisions. So the number of possible collisions has gone up by 2, even though we've only added one more molecule. We add another molecule of B, now we've gone from 6 possible collisions to 9 possible collisions. Okay, so raising the concentrations, it's again the product of the concentrations, not their sums. All right, we've talked about this as well, temperature and the rate constant or rates. So temperature has a big effect on the rate. For many reactions, increase of small as something like 10 degrees Celsius will double or even triple the rate. Okay, why is that? Well, K, the rate constant, is increasing exponentially for many reactions as temperature increases. And so this is expressed in what's known as the Arrhenius equation. And the Arrhenius equation is the equation for the rate constant, and that equals A, which is the Arrhenius constant, times E to the negative EA over RT. So what is that? Well, again, little k is the rate constant. A, that constant is a frequency factor. EA, E sub A, is an activation energy, what's known as activation energy. And R and T, R is the gas constant, T is the temperature. So a higher temperature gives you a larger K and thus an increased rate. If we look at this, how this happens, here we have 4 experiments. They have the same concentration of reactants. The temperature now is increasing by 10 each step. And then the rate that you see, it almost doubles from here to here. Okay, so that's a big jump in these rates. And that's primarily due to this rate constant. You can see that it is also doubling, or basically doubling, from experiment 1 to experiment 2. So in that Arrhenius equation, that term E sub A, it's known as an activation energy. So if you go back to that equation real quick, you can see that if that's the larger this value is, because E is raised to the negative power here, so the larger EA is, the smaller K is going to be, and thus a smaller rate. So this activation energy is really like a threshold that you have to overcome to be able to effectively follow through on the reactions. Right, the lower the activation energy, the faster a reaction can occur because that barrier is just, it's not as big, so it's easier to overcome. Right, so the smaller that EA is, the larger the frequency of effective collisions you can have, thus the larger your rate constant would be and your rate would increase. If you want to think about that in terms of, like a way to represent that in a picture, your activation energy, if you had the energy of your reactants and products shown here, right, that's a downhill jump, right? You should be able to easily do that. The problem is you have to reach an activated state. You have to reach your a transition state between reactants and products for the reaction to happen. So there's this positive energy you have to overcome before you can lose and drop into your products. Now, if we think about temperature and collision energy, right? As temperature increases, the motions of the molecules or particles is going to be increasing. It's going to be faster, and that means they have more kinetic energy. So that leads to more frequent collisions, and it leads to an increased reaction rate. So if they're moving around faster, they're going to collide more frequently, and also at higher temperature, the fraction of collisions, they're going to have more energy because they're moving around faster. So the fraction of collisions that have enough energy to overcome the activation energy will also increase. So it's really like a double reason why the temperature is increasing rates. And this just shows here two reactions, to reaction at two different temperatures. So at T1, this is the amount, the fraction of collisions, and let's say they have to have above this activation energy. So all of these in the shaded kind of purple region, those would be the fraction of all these collisions that have enough energy to overcome that barrier. Well, if we raise the temperature, it sort of spreads this plot out. And what happens is now that this red, shaded red area is what the fraction would be that have enough energy for overcome the activation energy barrier. Okay, so you'll have a bigger fraction of collisions that actually result in a reaction. If we're plotting, this plot here shows the effect of activation energy and temperature on the fraction of collisions with sufficient energy to allow a reaction. So if we do activation energy, right, if we're increasing activation energy, that's a bad thing in terms of trying to get a reaction to go, right? You're making the barrier higher, and that's shown here. The fraction of collisions at 298 Kelvin with enough energy to overcome that get less and less, right? And you can see exponentially, they really go down. We go from 10 to the minus 9 to 10 to the minus 18 by doubling that activation energy. Likewise, when you raise the temperature, the fractions are of collisions that have enough energy to overcome that barrier go up. The activation energy can be calculated from the Arrhenius equation. So if we're given our rate constant, and we know the Arrhenius equation, we can kind of solve this and rearrange it to a straight line form, which would be the ln of k equals the ln of A minus activation energy over R times 1 over T. And so if you have data available at two different temperatures, how that would look, this is typically how we use it. We'd have the ln of K2 over K1 minus EA over R times 1 over T2 minus 1 over T1. So this is typically how we would use the Arrhenius equation. We can plot this data graphically, and if we plot ln of k versus 1 over temperature, we get a straight line with it. That intercept is going to be ln of A, and the slope will be minus EA over R, right? Because this is y equals mx plus b. Sorry, mx plus b. It's written a little bit backwards there. Okay, so let's try our final practice problem using the Arrhenius equation. Okay, so we have decomposition of hydrogen iodine showed here. It has rate constants of 9.51 times 10 to the 9th liters per mole second at 500 Kelvin, and 1.1 times 10 to the minus 5 liters per mole second at 600 Kelvin. Find the activation energy. Okay, so we're given K values, 2 K values, and we're given 2 temperatures. So we have enough information here to use that Arrhenius equation. So we have ln of K2 over K1 equals minus EA over R times 1 over T2 minus 1 over T1. So now we need to rearrange this to solve for the activation energy. So we could do, first we can take both sides and divide by 1 over T2 minus 1 over T1. So we'd get negative EA over R. Then we can multiply both sides by R. So we'd have ln of K2 over K1 divided by 1 over T2 minus 1 over T1. That whole thing times R would be negative EA. And then you could just multiply both sides by minus 1, right, to get rid of the minus on the activation energy side, put it on the other side. Okay, so that would be our equation. So if you plug in those K values and the temperature values, and then R is just the gas constant. And so the form we want to use here for this is 8.314 joules per mole Kelvin. Okay. So you typically see this written in different ways, but for kinetics, we typically want it in an energy in this Arrhenius equation, right? Because we're dealing with the activation energy. So we want it in this form in joules per mole Kelvin. And when you do all of this and plug everything in, you should be getting an activation energy something like 175,900 joules, or 1.76 times 10 to the 1, 2, 3, 4, 5 joules. Okay, so that is the end of that material. In our next lecture, will be our last lecture of the quarter, we're going to talk about catalysts and how catalysts speed up reactions. And they do that not by changing the thermodynamics, so not by changing the energies of the products or the reactants, but they lower the activation energy and thus make it easier to go between reactants and products and thereby speed up the reaction.